Hello, and welcome to the lecture on Chapter 10 from Astronomy Today. We're going to continue talking about the planets of our solar system with the next in line, Mars. All right, very exciting planet to talk about because Mars is regularly in the news. Perhaps you've seen these stories about rovers on Mars. So let's learn a few interesting things about this neighboring planet to Earth. Okay, so what are the topics we're going to cover? Well, as we do with all the planets, we're going to talk about orbital properties, the physical properties of the planet, long distance observations of Mars, the Martian surface, then something specific to Mars. Is there water on Mars? Was there water on Mars? Is there or was there life on Mars? More likely, was there life on Mars? Then, as we do with many of the planets, we talk about the Martian atmosphere, the internal structure, and Mars has a couple of small moons, so we will briefly discuss those moons. Okay, so let's get on to the content of this chapter. Okay, so here's Mars's orbit. Now, one interesting thing about Mars's orbit is it's fairly eccentric, okay? Now, it's not a dramatic eccentric orbit like a comet, but it isn't a perfect circle either. And when we say eccentric, we mean deviation from a perfect circle. So the more elliptical, the more eccentric. The less circle-like, the more elongated that ellipse, that is more eccentric. Okay? It's the term given to that stretching of a circle into an ellipse. That does affect the sunlight that reaches the planet. And this eccentricity of the Martian orbit can be shown here. Consider the sun at the center of this image, the image on the left. And if we look at the Martian perihelion, that is when Mars is closest to the sun. And if we look at the Martian aphelion, that is when Mars is furthest from the sun. And we can see the difference is quite substantial as compared to Earth's orbit around the sun. All right, so notice that when Mars is at its aphelion, its furthest distance from the sun, it is 0.6 astronomical units from Earth, or at least from Earth's orbit. Earth may not be at that exact location, right? But you get the idea. But when it's at its perihelion, it's only 0.37 astronomical units. And we could, of course, find the total distance of Mars from the sun by summing the distance from the sun to Earth, and then all the way to Mars. And in this, so we would get, for example, 1.38 astronomical units for perihelion and 1.67 for aphelion. That's a pretty big difference. That's a much larger percentage difference than Earth's orbit. And it does absolutely affect the seasons, okay? Because Mars has an axial tilt, but it also has this more eccentric orbit than Earth. And that means that its seasons are more extreme because there's going to be moments in the year where the southern hemisphere is getting more direct sunlight due to the axial tilt, but Mars is also closer to the sun in the summer, so we have a doubling effect. We have more intense sun because of the proximity of the sun in space, and we have more direct sunlight because of the tilt of the planet and the path of the sun through the local sky. So in other words, the southern hemisphere gets hotter summers and colder winters. Now, that could be true on Earth as well, but it doesn't bear out. We don't have any deviation between the southern and northern hemisphere between the seasons. Mars does. Okay? All right. Furthermore, talking about viewing Mars from afar, Mars can be located either in the general direction of the sun, which is conjunction, or away, opposition. And that's because, unlike when we talked about Mercury and Venus, Mars has an orbit that's outside of the orbit of Earth, right? So we see here, there's Earth, there's Mars. And because of that orbit that is greater than the Earth orbit, that means that we could see Mars at midnight because we could have a position where Mars is on the other side of us. We would see it in the middle of the night because we're looking away from the sun. Okay? Now sometimes we have to look at the sun to see Mars. Of course, you wouldn't be able to because it'd be washed out by the sunlight of the sun, unless maybe it's an eclipse or something, or you have a special telescope. But regardless, there are certainly times where Mars is behind the sun. Okay? All right. So that's the idea between the orbits of Earth and Mars and the observations of Mars. Okay? All right, so some facts, some physical properties about Mars. Well, it has a radius of 3,394 kilometers, okay? Now compare that to Earth, which is about 5,600 kilometers. It's definitely a smaller planet than Earth, and if you recall, Venus is about the same size as Earth, in terms of its radius. So we can then say that Mars is smaller than both Venus and Earth. Okay? All right. It's not the smallest of the terrestrial planets. That is Mercury, but it is certainly smaller than either Venus or Earth. It does have the two moons. We'll talk about those at the very end of the lecture again, Deimos and Phobos. It has a mass of 6.4 times 10 to the 23 kilograms and has a density of 3,900 kilograms per cubic meter. This density is less than the density of Earth. Okay? And it has a length of day that is, well, about the same as Earth. Okay? That's really close to our 24 hours, right? Which is to say, it's really close to the length of the day. So we could use T for a period, a time of the day for Earth. Okay? Yeah, well, that's pretty cool. We haven't seen that because we've had very unusual days. We had Mercury with its 60 Earth day. We had Venus with its essentially year-long day. It takes about some 360 Earth days to have one Venus day. So these really dramatic deviations about the actual rotation of these worlds around their own axis, but not Mars. Okay. Now, and that is certainly part of the desire to go to Mars because we would have a nice light darkness cycle if we were to, say, have a base on the surface of Mars, a human manned base. Okay, so more about long distance observations of Mars. Well, one thing we can see from afar are the polar ice caps, and they grow and shrink with the seasons. Okay, so we can see some better images with close-ups, but we certainly see this very large polar ice cap in the winter season of the Northern Hemisphere, and then a significantly shrunk polar ice cap in the summer season of the Northern Hemisphere. And the southern polar ice cap, so the one down here, follows the same process, just opposite times of the year. All right? And furthermore, they're quite similar between the two polar ice caps, except that the northern ice cap has, as far as we can estimate from this, basically the particular signals of reflecting light off of these, and then looking at the atomic fingerprint of what's in these substances, that because we're not going there and taking direct samples and bringing them back to Earth, not yet, but we can reason out that the northern ice cap has more water in it than the southern ice cap. But let's talk about the actual composition of these ice caps, because these changing polar ice caps, right, the ones that shrink with the seasons, are frozen carbon dioxide. That's the part that freezes and melts in the seasons. Now, underneath that seasonal layer of frozen carbon dioxide is a permanent layer of water ice, especially in the northern ice cap. Okay? Now, in addition to features that we see on the surface of Mars that we could see from a telescope based on the surface of Earth, we notice that there's shifting dust. It makes the surface look like it's changing. Okay? And in fact, 100 years ago, scientists speculated that maybe there was vegetation on the surface of Mars because there was such dramatic differences. It looked maybe like, large plains of grass growing in the summer and then dying off in the winter. But in fact, it turned out it's just these large dust storms, because there are particular seasons where the dust storms become incredibly active, and that can lead to these dramatic events of layering of dust, all right, and shifting of it. Okay, so very high winds and dust storms. Okay, but there are reprieves as well, which is good for maybe missions to Mars. There's times of the year where the dust storms are very infrequent. You just have to be able to hunker down, whether it's a rover or in the future people on Mars, during the particularly windy active dust storm times of the year. Okay, now what about the Martian surface? As we put probes into orbit, as we land on Mars, as we learn more about Mars with better telescopes, as we even have flyby missions past Mars that take these beautiful photographs like this one here, then what do we know about the surface? Well, quite a bit. There's some interesting facts, and there's some overall trends as well. So the major features, the overall trends, is that there is a large continent-like structure called the Tharsis Bulge, which is about the size of North America. It's 10 kilometers above its surface. Think of that as almost like an ocean shelf, where the continents are about 3 kilometers on Earth above the basin floor of the oceans, the major oceans of the Pacific and Atlantic. Okay, that Tharsis Bulge has minimal cratering because it is the youngest part of Mars. So whatever created it, some volcanic or crustal activity, it has not been cratered much since. And again, the whole story about cratering, because this comes up so much when we talk about the age of the solar system, is that cratering isn't an ongoing process. Not really. Yes, there are still asteroids out there that crash into planets, but it's so infrequent compared to that era of bombardment. If you remember me talking about that. So that really tells us that we can look at ancient surfaces of planets that were around during those first 500 million years, which was the era of bombardment, and we can tell because they're covered in craters. That's like the moon and Mercury. And then anything that was created after that is going to have infrequent craters. So it's kind of like this bifurcation. It's either really old, about 3.5 billion years old, or it's more recent than that. And of course, you can get more detail, but that is the general division between cratering. Okay? All right, so let's talk more about those major surfaces or major features of the planet. Okay? So this map shows the surface features of Mars. It's color-coded in that the lower elevations are blue and the higher elevations are red and then eventually white with the very big peaks. Okay? There's no evidence of plate tectonics here. So we don't see shifting plates or continental plates or ocean plates or anything like that. But we do see, obviously, a big difference between the north and the south. The northern half of the planet is low elevation, has very few craters, right? Just a couple of them here, but very few craters, okay? So very little cratering, which means it's more recent. It's been resurfaced more recently in terms of hundreds of millions of years or a couple billion years. And as I said, it's lower elevation, whereas the southern hemisphere down here is higher elevation and older, more cratered. Okay? All right, so that's a big difference between the two, between the north and the south. Now, in summary, kind of about the Martian surface, we've got the northern hemisphere. It has rolling volcanic terrain, all right, so something like this, shown on the left. The southern hemisphere, on the other hand, is heavily cratered. It's got those highlands, okay, an altitude about 5 kilometers on average above the northern, okay, so much higher. Now, some parts are even higher, like the Tharsis Bulge, which is 20 kilometers, so really, really big, okay? And the assumption is that the northern surface is younger than the southern. And that's a very reasonable assumption compared to all the trends we see between planets, right? It's our whole idea that there's this overall behavior of the solar system. We piece together the evidence as scientists, okay? And this means that the northern hemisphere must have been lowered in elevation and then flooded with lava, okay? So what caused these processes? What does this tell us about the history of Mars? Well, we'll talk a bit about that, okay? So some other interesting things about the Martian surface, just some inevitable takeaways. It's like, oh wow, that's cool. Is there's a giant trench or a giant canyon on Mars and some really big volcanoes. So the Valles Marineris is a huge canyon created by crustal forces, not plate tectonics, but just some cooling and overall movement of the crust on a planet-wide scale. And it created this huge canyon that's 4,000 kilometers long and up to 120 kilometers wide. All right, and dramatically 7 kilometers deep, almost an Everest depth, deep, deep down in this canyon. It's just hard to imagine what it would be like to be standing on a canyon that vast. And to scale, look, here's the Grand Canyon. All right, the Grand Canyon to scale is just a little sliver compared to the sheer size of the Valles Marineris. Okay, the biggest canyon on Mars, much bigger than any canyon that exists on the surface of Earth. And it's not because there's not, there's weather features here, right? So it's not like this, it's not like we can just say, oh, we don't have canyons this size on Earth because it would be weathered away or worn away. Maybe we just don't have such large canyons on Earth because plate tectonics don't lend themselves to them. But for whatever reason, we have this huge, huge volcano that exists on Mars. Okay, well, I said volcano because I'm thinking ahead, but of course here, this is a huge canyon, okay? Now on to the volcano, okay? So Mars has the largest volcano in the solar system. Perhaps you've heard of it. It's one of the famous facts about Mars. It has a great name. It's called the Olympus Mons, all right? It has a 700-kilometer diameter base. So, it's a volcanic base that's the size of some states. It's just this huge, huge volcano, one huge mountain. It's 25 kilometers tall, all right? So that puts it at over twice the height of Everest. Its caldera, so just kind of the center itself, is 80 kilometers in diameter. That's just the part that's caved in, all right? And to give you some perspective, there are actually 3 other Martian volcanoes that are only slightly smaller. So, I mean, and all of those are bigger than any volcano we have here on Earth. So Is Mars just a planet of giant features? Well, not necessarily. There are different processes that could lead to this really big canyon and this really big volcano. The really big volcano, Olympus Mons, and its sister volcanoes that are also quite large, is really a testament to the type of lava being very viscous and the lower gravitational force on Mars. Because gravity on Mars is about 1/3 the gravity on Earth, which means that things are able to hold together because there's less force on them. That allows for larger mountains to be built up and not collapse under their own weight. Okay, so that 1/3 gravitational acceleration means 1/3 weight, which means bigger things can be supported by the crust, and that's part of the reason. A volcano this size on Earth would weigh so much that it would literally sink into the crust, kind of pushing the crust down into the mantle, so it couldn't really be supported. Okay. There's a limit to the size based on the greater size of Earth and thus the greater gravitational acceleration and resulting weight. Okay? All right. So now we're moving on to this specific topic about Mars, water. Does Mars have it? Well, let's think. Was there ever running water on Mars? Well, most people say yes, okay? I mean, really, the scientific community is pretty much in agreement. Yeah, there's tons of evidence that there was once liquid water on Mars. How much there was is, the details are certainly debated, but there's so much compelling evidence. All right, let's talk about some of that. So there are runoff channels that resemble those on Earth, right? What kind of feature would make this? Water. All right, now these are left up. They've been dry for billions of years, just dry, being covered by dust every Martian year, right? And then the dust gets washed away the next year, depending on the season. But these previous river valleys have just been sitting there dormant for billions of years, or at least that's what we think. Okay, but still the feature remains. They look like river channels, and there's no other reasonable explanation to how they could have been formed. Okay, and it's comparing Mars and Louisiana. All right. Furthermore, we see existence of what appears to be rivers and lakes, catastrophic floods that occurred around 3 billion years ago. And this number of about 3 billion years, that's when we think liquid water last existed on the surface of Mars, about 3 billion years. Long time. You think like, wow, I mean, 3 billion years, like how do we even find evidence of something that's 3 billion years old? Well, it helps that there's no plate tectonics, and it helps that there's been no water since. The only thing that's been really kind of cleaning the surface and destroying the evidence have been those dust storms and the high winds. But there's still a lot left over, even after 3 billion years. Okay? So this right here may be an ancient Martian river delta. Okay? That alluvial fan, if it's a term that comes up in geology, when you have a delta and that delta is distributing sediment, it does in this kind of fan shape. We see a lot of evidence of that here on Earth in watersheds when they spread out at the opening of a river. And this has those same characteristics. This is not a lava flow. None of the rocks are volcanic. There's tons of sedimentary rocks. And we're starting to learn a lot more about that because in just such a river delta as this, just over a month ago, the Perseverance rover actually landed near, not this particular river delta, long dead river delta, but a similar one, and is going around and sampling the rocks and exploring the terrain and really, making sure that we're not completely wrong about this theory that this is a long dead river delta by, really going through there and taking chemical samples and all that, getting all that detailed data. All right, and actually getting chemical fingerprints by bouncing laser light off of rocks, so we know exactly what elements are in the rocks and all types of sophisticated techniques. Okay. So very, very, very interesting current science going on with the Perseverance rover. Perseverance rover. Okay, just recently landed on the surface of Mars, been a huge success so far in terms of the mission. Okay, now remember that northern southern hemisphere? Well, the northern hemisphere, which was lower and then obviously covered in lava at some point, well, the reason it might have been lower was it would have been sunk down by the weight of an ocean on top of that. We see that with our own planet. We see that the oceans affect the crust underneath. And it's a thinner crust because it's compressed down by the ocean. It's been a long process, between liquid water on the surface and the whole nature of the crust. But it's true. Oceans bring the crust down. So that would be a good explanation of why the southern hemisphere is so much lower. Is there once was a giant ocean that covered the northern hemisphere. All right, we can zoom in on bits of it. Furthermore, impact craters less than 5 kilometers across have mostly been eroded away. Okay, So such dramatic erosion in the northern hemisphere, again, a testament to liquid water at some point. Analysis of craters allows estimates of the age of the surface, and cratering on the right, like this one, was made when the surface was liquid. Now that could have been volcanic, right, rather than mud, but certainly there is a dramatic effect here where this was not solid rock that was able to splatter like this, all right? And it could well have been mud, right? Just a mixture of water and liquid, okay? More recently, goalies have been seen that seem to indicate the presence of liquid water today, because models suggest that the water actually mostly got pulled into the crust rather than escaping into space. Like we can make an argument for, that mercury can't retain water because it's going to escape into space or to get boiled away. Well, that's not the case in Mars because of a number of factors, including the further distance from the sun. And so Mars seems to have maybe collected its water, kind of frozen it, had it sink down into the crust. And maybe there are places that are particularly warm where that water still bubbles up in a muddy slurry and then creates ongoing water features, okay? And we can see pictures between 1999 and 2005 taken in orbit above Mars that actually show variations in the goalies, that the goalie formation is ongoing. So suggesting that, maybe there really is still liquid water flowing in little pockets, or at least, bubbling up in muddy messes on the surface of Mars, okay? Okay, and some water may now be permafrost under the polar ice caps. We say may to be cautious, but certainly evidence highly suggests that there is lots of liquid water in the caps, all right, but under that frozen carbon dioxide. The southern polar cap is mostly carbon dioxide. That one doesn't appear to have as much water, but the northern one certainly has a lot of water with just that seasonal layer of frozen CO2 on top, all right? And then, and we can, the images are taken during the local summer, the images that we show over here, showing that leftover frozen water, okay? All right, furthermore, Viking landers both landed in the low latitude northern plains, rocky surface, red due to the iron content. There's a lot of iron on the surface of Mars. I'm gonna come back to that idea, so hold that thought. Why is there so much iron on the surface of Mars? Here's Viking 1 photos. These are kind of legacy missions from really early on when we first landed on Mars. Viking 2, all right? Now onto more recent missions to Mars. The landing site for Opportunity, this is in the early 2000s, was chosen to maximize the chances of finding water, or at least evidence of water, okay? Now, there's been lots of pictures of rocks that appear to have been weathered in streams and, all this indirect evidence of water, but no, we're not actually finding, any bubbling brooks or anything, okay? The Curiosity rover, all right, landed on Mars in 2012. The mission is still ongoing. It recently reached its 6,000th Martian day of taking data and still rolling around. So it's amazing it's been going so long. Such a huge successful mission. The one I talked about before, by the way, was Perseverance. Curiosity is essentially the forebearer to Perseverance. They're very similar rovers, just with Perseverance having some more bells and whistles and being a more fancy rover, and one that just landed a month ago. Okay. But what Curiosity has been doing over the last 9 years has been looking for evidence of water on Mars by searching for carbonate rocks. Okay, so it's been a very rock-focused mission, going around taking photos and analyzing rocks. Okay, now it's not like they have a full lab inside the rover, but they can still do measurements by reflecting light off the rocks and so on. Okay. The Viking Landers looked for evidence of living organisms, but did not find anything conclusive. Okay. Furthermore, 2 Martian meteorites found in Antarctica show possible signs of microbial life, but the evidence is disputed. So I wanted to come back to this because this is a famous, kind of research finding, and really there's no permanent conclusion, right? Like here's an image of the structures that were found within the rock, and we think, well, is that a fossil? We're just not sure, right? And we just have this one sample, and so the scientific community is just we're just some people feel strongly, yes, that is a fossil, but then the chemical makeup is there's no clear DNA or anything, so we just don't know, right? And we have the problem that this is a Martian meteorite, so you can so like it's like, oh well, did something get fossiled after the fact? Like how long ago did it land on Earth? Because the idea is the reason we could have a rock on Earth from Mars without going there and getting it ourselves is, imagine you have a very large asteroid crash into the surface of Mars, throw off rocks of such speed that those rocks themselves become new meteorites, basically breaking them loose and giving them enough velocity so they escape the gravitational pull of Mars. Then some of those rocks drift out into space, get caught by Earth's orbit, and then fall onto Earth. And that happens. It's an ongoing process. Meteorites that come to Earth occasionally have originated on other planets, and it's always a great finding. And that's the story behind this one here, found in Antarctica. Okay. Now that Perseverance rover, all right. So the Perseverance rover, one of the things that it wants to do, one of the greatest accomplishments, hopefully in quite a few years of that rover, is it has a bunch of little sample tubes on board the rover. And again, the rover looks something like this. And it's collecting rocks, putting them into those sample tubes. A mission in about 5 years is then going to go there and collect those sample tubes, launch them up into space where they're going to get caught by another orbiting probe that's then going to bring them back to Earth. So we're actually going to be bringing back samples in about 7, 8 years from Mars, and we've never done that before. And we're going to bring back the samples that the photos suggested might have fossils in them. And this is going to be that key moment. If we can find conclusive evidence, very carefully collected conclusive evidence of fossils on Mars, then we will know finally and definitively that life is not unique to Earth. Okay, even if that life is long dead on Mars, that would be a final argument, that they would be done. It'd be like, nope, okay, we know for a fact that there's life somewhere other than Earth. Okay, all right. So done with life, done with water. Let's talk about some more of, kind of wrap up with some final interesting facts about Mars. About Mars, excuse me. And then one thing we always talk about with our planets is the atmosphere. So what's the deal with the Martian atmosphere? Well, it's mostly carbon dioxide. It's very thin. So it's there. There is an atmosphere that we should guess there is because there's dust storms, there's wind. You have to have a gas in order to have wind. So there's no wind on the surface of the moon because there's absolutely no atmosphere, okay? Or just like, so little to speak of. So the Martian one is there, okay? It's a thin atmosphere, definitely too thin to breathe and doesn't have the right composition to breathe, okay? And it's also so thin that it doesn't retain much heat, okay? So the Martian nights become very, very cold. The temperature falls off. And even the Martian days, although they're sunny, all right, and you see that in photos taken on the surface of Mars, they're sunny, they're not all that warm. So the temperature kind of maxes out on the surface at about 250 Kelvin, which is, like in maybe like, negative 20 Celsius. And so, it's cold on Mars. It's just thin atmosphere. And then it's even colder at night. Okay. So, certainly it's not warm enough to, kind of to not be inside a dome or underground or something like that. Okay. But again, it's not nearly as hostile as say Mercury, which is much, much colder at night, or, certainly not as hostile as Venus, which is just always hot, metal melting hot. So it's kind of, it's a dramatic climate, but not nearly as much so as the other worlds we talked about. Even the kind of the surface atmospheric conditions of Mars are less dramatic than the moon, because the moon has that day-night cycle where it has about 14 days of darkness, 14 Earth days of darkness, and then 14 Earth days of light. And that means that it's dark for so long and it's light for so long that creates kind of a hostile atmosphere on the surface of the moon as well. Right, and let alone no atmosphere at all, and that's part of the reason we always could think about, can humans survive on Mars? Can we build permanent inhabited bases there? Maybe we can, okay. But I'll get a little off topic. Let's talk more about the atmosphere, okay? So we've got, the pressure variation, right? So we have, this is in Earth's atmospheres. So you can see that the pressure is, is pretty low. So even at its greatest pressure, it's about 6,000ths the pressure that it is on Earth. So very low atmospheric pressure. All right, so it's kind of there's a vacuum effect, so that's why if you pop the hole in your spacesuit on Mars, the air would start sucking out just like it would in space, because even though this isn't a vacuum, it's again, it's only 1,000ths the pressure on Earth, so it's like a vacuum, okay. And then but it does support clouds, so there's water ice clouds, there's carbon dioxide clouds at about 50 kilometers above the surface. The temperature falls off as you go up into the higher surface, and then it shoots up again. It shoots up for the same reason that we see with a lot of the atmospheres. This is because of absorption of X-rays. Okay, so it's high temperature up here, but up here the pressure is so low that it's high temperature in the sense of having a couple molecules per cubic centimeter that are moving very quickly, but there's no heat to be retained because there's just so few molecules. in terms of such dramatic density, such dramatically low density in terms of the gas. Okay, so that's kind of just a quick summary of the atmosphere. All right. Fog can build up. So there's fog. This is like a ring of fog building up in a crater. We can see evidence of fog here as well. So that's kind of neat because that's something that we'd associate with with Earth, right? But this is carbon dioxide fog, right? Kind of condensing, being frozen, like we imagine water fog on Earth. Okay, or as we're familiar. Now, an interesting thing about the Martian atmosphere and the story behind it is it's kind of like a reverse greenhouse effect, and I think this slide does a good job of summarizing that. So Mars may be victim of a runaway greenhouse effect, but in the opposite way of Venus. Because Venus, what happened is it just kept retaining and retaining those greenhouse gases, which allowed more and more heat to be held in, which made the planet get hotter and hotter, and then that basically melted things and evaporated all the water, which then made it even hotter than it was before, and now it's stuck hot. But on Mars, instead, as the water ice froze, Mars became more and more reflective. All right, because it had a more and more reflective surface, and then its atmosphere became thinner and thinner, right? As it's reflecting more and more heat away, freezing more and more water, which then progressively makes it more reflective. It's that feedback loop, where one thing leads to another, and then eventually the carbon dioxide started freezing as well. So we had a process where Mars got colder and colder due to this feedback loop, this runaway effect. Okay. So then that means that Mars may have had a much warmer surface and a much thicker atmosphere a few billion years ago, back when liquid water would have been around. Okay. So as a result, Mars may have had a thick atmosphere and liquid water in the past, but they are now gone due to that reverse greenhouse effect. Something that takes a long time to happen, but then we're looking at the eventual effect. And so it is so interesting then to think about that we have these two planets on either side of Earth in terms of their orbits, one interior, one exterior, where Venus had a runaway greenhouse effect that led to it being unbearably hot, and then Mars had a runaway greenhouse effect that led to it being cool and having a thin atmosphere and not supporting liquid water. And that balancing act where Earth was able to keep things balanced just right, but it's such a precarious balance. We see with our neighboring planets that things can go wrong so easily. Okay, now let's talk about the structure, because I promised I'd come back to the idea of the iron on the surface. So no seismic studies have been done. And that's interesting because we tried. Between the Curiosity rover and the Perseverance rover, there was a lander, so not a rover of wheels, but just one thing that lands and stays in place, called InSight. And the InSight lander was actually supposed to do seismic studies. It had a device called the Mole that was going to dig down to the surface. But it turned out that the one place where it landed had denser ground than anywhere else that had been sampled in previous missions. And the Mole was not able to dig down. So we still do not have good seismic studies about how many earthquakes, if any at all, occur on the surface of Mars. So it's an open question. But from the behavior of the crust, based on the images and the kind of the models that we can come up with, it's estimated that the crust is about 100 kilometers thick. Underneath that would be the mantle. But there's no magnetic field, just none. Okay? Now, that's really interesting because we've seen no magnetic field before. We saw it with Venus. Okay? Now, Venus probably doesn't have a magnetic field because it rotates so slowly. It's got that Venusian year that is 360 Earth days long. Okay? Or Venusian day, excuse me. But why does Mars not have a magnetic field? Because it spins quickly enough on its own axis that it could support one, because that's one of the ingredients to supporting a magnetic field. Well, maybe it's because its core has no metal in it, okay? Or maybe it's because its core isn't liquid, although we suspect its core is liquid, all right? Or maybe it's neither liquid nor metallic. But the most likely explanation is that it's not metallic. And that's because what scientists think is that iron on the surface is part of the reason, or part of the evidence, that the core isn't metallic. Because it's thought that because Mars is smaller and didn't heat up as much in its primordial phase, so when the solar system was being formed, that it never became fully liquid as a planet. And that means that it never had an opportunity for the denser metals to sink down into the core. Because we have iron, some of the densest common metals, that sunk down to the core of our own planet when Earth was in a completely liquid stage, a completely molten stage. If Mars never had a completely molten stage, its iron never sunk down to the surface, which is why there's so much of it on the surface, making that reddening effect, all right? And because of the rust oxidation that led to all the red surface, the iron-rich surface, and means no metallic field, or no magnetic field, because no metallic core. Okay, so you see how those ideas are closely related. And so it's a good explanation because it explains two things at once. Okay? All right. So finally, the moons of Mars. There's two tiny moons. All right. Phobos is about 20 kilometers by 20, and then Deimos is only about 16 by 10. Right. So they're quite small. They're like asteroid size. All right. Deimos actually is probably a captured asteroid. Phobos, on the other hand, actually may have been part of Mars based on its density and composition, and actually got flung into space, kind of like the way our own moon was formed, but in a much less dramatic fashion because it is much smaller. All right, so that's the idea of Mars's two moons. And they're both so small that you wouldn't even see them with the naked eye in the night sky of Mars. Okay, but they are officially moons. Mars has them. Okay, so in summary, Mars orbit is more eccentric than Earth's. That does affect the seasons. Okay, because our Mars also has an axial tilt that's comparable to ours. It rotates in 24.6 hours. Its axial tilt, as I just said, is similar to Earth's. The atmosphere is very thin, mostly carbon dioxide, right? It's only about, 0.6% as thick, right? Because it was six thousandths as dense, okay, the atmosphere. The temperature is around 50 Kelvin, or 50 Kelvin below Earth's, okay? So about, the average temperature, instead of being, 20 Celsius, is about, as I said, about negative 30 Celsius on average. Okay, but the seasons are similar. There's a warm time of the year and a colder time of the year. The Mars landers have yielded substantial amounts of data, right? And I've kind of come back to that, right? The landers and the rovers, right? We've learned so much about Mars, and we're really continuing to. This is a golden era of Mars research. All right. The northern and southern hemispheres are very different. Okay, we talked quite a bit about how they're different. The southern is higher and heavily cratered. The north is lower and relatively flat. And where did the ocean used to be? Right. So the potential previous ocean would have been in the northern hemisphere. The major features, we got that really high continent, the Tharsis Bulge. We have Olympus Mons and Valles Marineris. The crater ejecta provided evidence for permafrost layer under the surface, all right, which was easily liquidized, and the two small moons. Okay, well, that finishes up Mars. I hope this lecture has been interesting and informative. Thank you so much for watching.